Good evening, friends. Today I would like to talk a little about the great scientist Sir Isaac Newton. You know, uh, the contribution of Isaac Newton to physics and science in general is so huge that it's never enough to talk about his contribution. When we talk about two of the biggest names of physics, probably they are Isaac Newton and Albert Einstein. Isaac Newton, he was born in 1642 and he died somewhere around 1726. He is widely regarded as one of the most influential scientists of all time. And, you know, he is the pillar of classical mechanics. He's a key figure in the scientific revolution. He wrote a famous book, his book Prince Philosophiae Naturalis Principia Mathematica. That is the meaning. The book is Mathematical Principles of Natural Philosophy. It was first published in 1687. It laid the foundations of classical mechanics. Apart from classical mechanics, Newton also made seminal contributions to optics, and he shares credit with Gottfried Wilhelm Leibniz for developing the infinitesimal calculus. You know, so much he had contributed to science, but he always remembered that uh, people have contributed in past as well. So what he said famously is, if I have seen further, it is by standing on the shoulders of giants. And as you can see here, this is the front page, the cover of the famous book, Philosophy Naturalis Principia Mathematica, generally commonly known as Principia Mathematica. I remember probably I had the chance of reading few pages of this book when I was a PhD student at Physical Research Laboratory. As you can see, the book was published in 1687 and the language was New Latin. Though he contributed to classical mechanics, calculus, he had similar contribution in optics as well. But the most famous and romantic story associated with Newton, which all kids learn when they are young, that when he was sitting under the tree, apple fall on his head, and he then, after thinking, in a way, discovered the theory of gravity. But if we strictly go by history, then we come to know that the story is slightly different, because there is a manuscript which is the biography of Newton. The title is Memoirs of Sir Isaac Newton's Life, which was written by William Stockley, if I'm pronouncing him properly. He was an archaeologist and one of Newton's first biographers. He published his biography, the biography of Newton, written by William in 1752. And Newton told this apple story to Stukely, who told it as, after dinner, the weather being warm, we went into the garden and drank tea under the shade of some apple trees. He was just in the same situation as when formerly the notion of gravitation came into his mind, and he was already in the contemplative mood. When the apple fall, it did not fall on Newton's head. He thought that why should that apple always descend perpendicular to the ground? And then, after much thinking, he discovered this law of gravitation. So if we want to know about the law of gravitation by Newton, it says that any particle of the matter in the universe attracts any other particle with a force which varies. The force varies directly as the product of the masses of the two particles, and inversely as the square of the distance between them. So the heavier the particles are, the more massive the particles are, the bigger will be the force, and greater is the distance between the particles, the less stronger will be the force. F is equal to G m1 m2 upon r square, where F is the force, G is the gravitational constant, m1 is the particle of mass of one particle, m2 is the mass of second particle, and r is the distance between the particle. This dot here is not the dot product. It is just telling you about the magnitude of the force. The direction of the force will be, they would attract each other, and it will be along the line joining the center of mass of the two particles. Besides gravity, during the forming the very foundation of the classical mechanics, Newton gave three laws of motion. The first law is every body persists in its state of rest or uniform motion in a straight line unless it is compelled to change that state by forces impressed upon it. It tells you that there are only two natural states of motion. Either it is the rest or it is the motion in a straight line. If any particle you are watching if it is at rest or it is moving in a straight line with constant speed, then there is no force acting on the particle, or the sum of all forces is zero. But if it is in any state other than these two, then it is under the it is experiencing some force. Second law is the rate of change of momentum is equal to the applied force, and if the mass of the body is constant, then the force is equal to the mass of the body times the acceleration in the body. But that would not be hold, but F is equal to ma will not hold when, because of when velocity becomes very high, it tends to the speed of light, then the mass of the body also changes. The body becomes heavier. So this relation will not hold there. The relation that truly represents the Newton's second law is F is equal to dp upon dt, where dp is the infinitesimally small change in momentum, and dt is that in infinitesimally small time in which that linear momentum change has taken place. The third law, very famous law, is for every action there is an equal and opposite reaction. Well, it means if a body applies force on another body, the another body applies the equivalent magnitude of force but in opposite direction to the first body.